Yes, Assalamualaikum and good morning, everyone.
Morning, doctor.
Okay, so today we will go for topic 7, which is organic semiconductor devices. Okay, so this is going to be the last device that we are going to study before we go on into characterization, measurement, the tools required uh, to study the properties of these devices. That one we will cover tomorrow. Okay. Okay, now organic semiconductor devices. We're going to cover more on the material itself, the organic material, the structure of the structure of the device. Especially, I'm going to cover on the transistor part. Basically, before that, we are going to look into the motivation behind why we are going forward into this type of devices, okay, organic type. Okay, so when we talk about organic, what is the first thing that comes into your mind? Anyone?
Biomass.
Apa dia?
Biomass.
Biomass. Okay. Organic. Yes. Because of the material that's produced from the biomass is organic. Okay. What else? That one kita buat semiconductor. Okay. What else? Chat. Original apa? How? Organic. Original apa? How? Okay, so you have the idea of when we talk about organic is the original, means that from the original source of the material. Okay. Cham Zongwei said something to do with carbon compound. Okay. Anyone? Last one? Last taker, organic. What else that comes into your mind? The first thing. You can put in the chat box if you want. Tak ada. Okay. If nothing comes into your mind, so I will just explain what do we mean by organic. But bear in mind, when I first get to know about this organic based devices, it is something that is not my favorable device. Okay, because one thing is organic material. Basically, we are talking about like what Zoe said, carbon based, those with hydrogen, carbon. This kind of chemistry is not something that I like. So I will try my best not to read about this article. Okay, that was a few years ago when I was doing my PhD. But then it took off very well because of the rising technology in the television, right? We have organic light emitting diode, OLED screen, and then you have uh, organic based devices. After that, it increases. Okay, more and more people are researching on this organic compound, but still the person who actually come out with the results are from chemists, not from those who have electronic engineers, okay, or electronic background like me. Because organic is not our forte, not our field, right? So those chemists, they come out in the journals of chemistry, journal of organic chemistry, they are talking about transistors. So we have to refer to chemistry, subject to study that what is this organic material is about. Okay, but it's very interesting in the end. Eventually, I found my interest, so that's why I decided to put into this course. Okay, so let's look at the overview of what is actually the motivation behind this organic field effect transistor. So when you see this term OFET, it's organic field effect transistor. So this OFET actually it enables the technology for plastic, paper, fabric-based electronics to enter the market. So it is different from silicon. So if you look at silicon, you have seen a silicon wafer, you can't actually bend it, right? So it's not flexible. So can we replace a silicon-based technology to a product which is more flexible? So that's the idea behind organic field effect transistor. And can we move from rigid substrate like silicon or other inorganic type to bendable substrate? And perhaps it is inspired by the Daily Prophet depicted in the Harry Potter series. Okay, if you are a big fan or avid fan of Harry Potter, if you have watched the movies, there's this newspaper which they call Daily Prophet, which actually the characters become alive when we are reading the newspaper. Okay, try to find the YouTube of one of the clips from the Harry Potter series, but I couldn't find. So this is basically how it looks like. In the movie, you can just watch in one of the episodes, like in one of the movies. Okay, the characters in the news while you're reading is actually become alive. So that's how perhaps inspire those scientists to come up with paper-based electronics or fabric-based or plastic-based. But then you know that in silicon, you can't grow silicon or you can't deposit a silicon material on a substrate like plastic or paper or fabric, right? Because silicon requires a high temperature process. A high temperature process can go up to 300 degrees Celsius. So by the time you have the silicon, the substrate becomes molten. Okay, you melt the substrate. So it requires a material where it has a semiconductor properties, but you can grow it at room temperature, or maybe the maximum temperature is less than 100 degrees Celsius. So that's the idea behind it. So what do you mean by organic? Organic materials, yeah, however, organic chemistry is the study of those substances containing carbon in combination with hydrogen and a few other nonmetals, namely oxygen, nitrogen, sulfur, and the halogens. So this is the type of material that we are going to deal with in our transistor. For example, the famous one is pentacene. Okay, this is a structure, pentacene. What is my arrow? The pentacene, right is perilene. And this is the famous type of organic semiconductor that people have been using to create organic type based devices. Okay, if you look at the chain, the molecules are longer. Okay, longer chain of molecules, and we will see the difference later on. But again, we are not going to go deep into the crystal properties of this type of molecules. It's just that I want you to know, aware of organic. When we talk about organic, it's like plastic. You know, the plastic cups, plastic thing that you are using, these are organics. Okay, polymer based. That we're talking about these materials can be used to make a transistor channel. Okay, what else? Those that you use in your pipes, PVC, okay? Polymer based. Okay, so it is very close to us, and they actually engineer this material to make it into a useful switching device. You have to aware that in organic semiconductor, there are two types. One is small molecules, another one is polymers. Polymers is the one that I mentioned, like plastics, something that have poly base. Okay, the name itself, it brings the polythiophene, PVDF, and so on. Other than polymers, they also have a material called small molecules. So polymers are long or large molecules, and small molecules are, for example, the famous pentacene. Okay, pentacene, which they use to make the devices. If you look here in the chart, the smaller molecules has a higher mobility. Okay, they can produce a higher mobility device compared to polymer base. Okay, but then they still prefer in some applications polymers because of its uniformity in covering uh, the the substrate. They are much more uniform. Can be the the reliability of this material in terms of uniformity in the distribution of this polymer on the substrate is higher compared to smaller molecules. Okay. Here it's mentioned here, reproducibility issues. Okay. So small molecule and polymer each have their own pros and cons, but materials and processes have improved tremendously for the past 20 years, and they keep on improving this. Okay, and the demand for flexible substrate, the demand for plastic, all these demands have increased. So that's why more and more scientists are researching on creating a new types of organic materials. Okay. Okay, these are some of the material. Perhaps you have seen some of these. For example, this one is OLED. Okay, if you have worked with Arduino or Arduino-based projects, you have used these organic light emitting diodes. Okay, this is different from the LCD display or LED display. And this is actually, cellophane tape. Yes, similar to cellophane tape. So they actually growing circuits on this tape, and they are just do a bonding between the one that they grow to the device substrate, which is the plastic base. This is another type of substrate. They put the circuits on a flexible substrate. Okay, they can actually print it. This part is studying more the properties of not only bending, but also how much is the strain, or how much it can withstand. Okay, how maximum you can bend the substrate before before it fails. Okay, so this is the type of characterization that they have to produce for bendable substrates of flexible electronics. And at the same time, the piezoelectric properties are also very interesting. Piezoelectric properties means it is sensitive with the pressure that you apply on the material. Okay, when you apply the pressure, it can produce voltage. There's some sort of power being produced. This is the type of uh, researchers that they have going through using organic based devices. Okay, so just imagine if you have a sensor, for example, if you have a sensor which you can bend, you can apply pressure, so you are actually generating, you are self-powering the sensor without using a battery. That's the whole idea. Okay, you just bend it, then it's power up. If you want to turn it off, you just unbend it. Okay, something like that. So these are the piezoelectric properties. And this falls under the topic of nano generator, okay? Generating its own power. It's very interesting. So the crystal properties is between organic and inorganic. As you can see, silicon champions in terms of the bonding is very strong, okay, covalently bonded, and it is very ordered. The atoms arranged in a very ordered manner. In terms of inorganic semiconductor, it is polymer-based organic material, so it is very weakly bonded. Okay, and they call it van der Waals bonded crystals. Okay, if you look at here, this is the long chain molecules that's being arranged in this crystal. Okay, so this is the organic. Advantages of organic electronics, again, as I have mentioned, it is much more lighter, more flexible. It has not, you don't have to use vacuum processing, low cost, no lithography, can just print it and can use different types of substrate like plastic, paper, or fabric. Okay. Another thing is low temperature. Forgot to add low temperature processing. So if you compare between organic and silicon-based technology, this is the comparison, whereby organic electronics, it comes in a very large volume with a large device size. The material of the substrate also flexible, required condition ambient, you can just continuously print on this substrate. Whereby in silicon, it requires a very clean environment, which you have to deal with ultra clean room. It is rigid, and the device size also very small. The cost to maintain the clean room, to get the material, silicon is expensive compared to organic. So it costs about 10 billion. It requires to have a photolithography process, right? So again, the cost, you have to look at the application as well. So if you're dealing with, remember we have discussed this, more than more and more. If you look into computational, memory devices, so far silicon is still the best. Okay, but we are moving towards more than more. So this is where the organic electronics comes in, giving spaces for different types of applications. Okay, if you look at the more than more application, you have RFID, flexible electronics, wearable devices. Okay. So if you look at the display, one of the biggest applications of organic transistors right now, okay, in display, like I mentioned, it started with display, the screen on your TV. Okay, how it becomes thinner compared to the Sony model, the previous model. So organic TFTs may be used to drive LCDs and potentially even OLEDs, allowing integration of entire displays on plastics. So it has a brighter display, it's thinner and it's more flexible. Okay, if you look at the LCD display, for LCD it requires a backlighting, but for OLED it doesn't need to have a backlighting because the organic material itself is self-sustaining in the to emit light, and also it can act as a switch at the same time. Okay, so it doesn't have extra circuitry behind this OLED. So that's why it becomes very popular to use in the screen display compared to liquid crystal display. Now, if we move into organic field effect transistor is such kind of FET using organic semiconductor in its channel. Okay. If you look at this structure, it's the same thing as what we have done before, like in semiconductor MOSFET. Okay, if you look carefully, the gold here act as the source and drain, right? And then you have pentacene. Remember I said pentacene is the organic semiconductor. So this is the channel. Okay, your semiconductor channel. The PMMA dielectric is your gate dielectric. Okay. PMMA dielectric is the gate dielectric. And ITO is the electrode as your back gate. Okay, this is the back gate, means that the gate electrode is at the back of your substrate. So this is the back gate configuration. And normally when we use organic material, the dielectric is also an organic. So that's why they use PMMA. Okay, there are some actually they use silicon oxide, but there are a lot of defects between the interface of the organic and inorganic. So normally if you use an organic material, the gate oxide they call it, and gate dielectric they use PMMA dielectric. Not PMMA, it's an organic dielectric, organic type. So in this paper I have taken, they use organic dielectric with a back gate, and this is your source and drain. And this is they have characterized and measured the transistor, and they have come up with the results, with the mobility results with different, I think with a different material. They try with a different material and plot it, something like that. I just want to show the structure. In the next slide, I have also a device structure. Basically, you have organic semiconductor. The source and drain is on top. This is top contact, and this is bottom gate. All right, so the gate can be ITO or other types of metal. The one at the bottom here is, it's a similar structure, but then no, it's a different structure, whereby the source and drain contact is at the bottom. This is at the top. The source and drain is at the bottom. So depending on what they want to do with the device, they have these two different structures of organic field effect transistor, right? And there are a lot of research going on with the different types of structures as well. They engineer with the different types of structure to get the best mobility that they can obtain from organic semiconductor. Okay. So this is another structure. This is top contact, okay, and bottom gate. So the gate they didn't use metal, but instead they highly dope the silicon until silicon is saturated with so many carriers. So this act as a gate, okay, because it has a very low resistivity. And the PMMA is your dielectric. This is 500 nanometer. PTV is your organic material. Okay, this is published in 2006. I've taken this paper. If you look at the characteristics, what do you think? Is this, what type of material is this? It follows the characteristic of like N-type or P-type.
P-type.
Type.
N-type or P-type?
P-type.
P-type. Okay, very good. Why is P-type? Because if you look carefully, if you follow the current with the voltage, the drain voltage is negative, and the current is also in this regime, okay, on the second quarter regime, third quarter regime of the IV plot. So this is a P-type organic semiconductor device. But if you can't see this one clearly, you look at the transfer characteristic. Transfer characteristic is the current versus gate voltage. So if the gate voltage is, if the current is increasing with the increase of negative voltage, so you know that this is a P-type. Okay, so this is a P-type substrate. In this paper, actually, they want to check how stable this organic semiconductor with in air. So that's why they do a double sweep. Okay, they sweep once and they sweep again. So there's two arrows going up and another arrow going down. Okay, they're sweeping the voltage. So it looks similar to typical transistor characteristic. Okay, but you'll be surprised that the mobility that achieved for organic this organic device is very low. It is the maximum that they have achieved so far. I think for this paper, it's only 1 cm squared per second. Okay, 1, or I think less than that. So if you compare with amorphous silicon, or with silicon or polysilicon, which has been reported previously, this OFAC, organic based transistor OFAC, is very low in terms of mobility. So that's why you cannot go towards more application. For example, in computational logic circuits and so on. Because switching, it's a no. Okay, very slow. It will just gradually increase and until up to it reach a saturation regime. But if they don't use it for more application, they are more interested to use this for other types of application because of the flexibility. So normally it will use in display electronics, for RFID or other types of that which doesn't require intensive switching. Okay, because there is a switching going on. You still can turn it off. You can still turn it on. It's just that it has a poor performance, right? Compared to graphene, where you can't just switch it off. So there is, even though you can achieve a very high mobility, but the basic element of switching is lacking for graphene-based devices. So that's why they need to engineer the graphene to make it nano ribbon. There are so many other types of approaches that they have used. Okay, so if you look carefully, organic semiconductor, you still can achieve a switching, but then the performance of the switching, okay, the mobility is lower. And the theory of transistor apply for organic FinFET transistor. Okay, even though it's an organic base, but if you look at this is a typical transistor equation, right? So you still can apply to get the mobility. W is the width of your W and O. So how does the organic semiconductor work? It is basically it has a carriers already inside this organic semiconductor. But then it needs to be forcefully induced. Okay, like any other semiconductor, you have to induce it. So if you look at this, if you look at this diagram, okay, if in inorganic semiconductor, they will call this LUMO, lowest unoccupied molecular orbital, as the conduction band, and your highest occupied molecular orbital, HOMO, as your valence band. Okay, but then in organic, I have looked into research papers and some books. They prefer to use this term, LUMO and HOMO. Okay, instead of using valence band and conduction band, because of the band structure of the organic semiconductor. Okay, so don't be surprised if you find these terms. Basically, LUMO is the lowest unoccupied, which is at the top, lowest unoccupied. HOMO is highest occupied, so it's mostly occupied with carriers, charge carriers. Okay, so if you look at the diagram A here, if this is where the Vg equals to 0, means that the gate equals to 0. So no charges are injected when Vg equals to 0. So there are no charges. So nothing happens. So at Vg less than 0, less than 0 means when a negative voltage is applied to the gate. So you are inducing positive carriers. Okay, positive charges are induced at the organic semiconductor or organic insulator interface, organic semiconductor, organic insulator interface. Basically, you are inducing positive carriers at the channel. Okay, this is the channel, right? So when Fermi level of the source drain metal is close to the HOMO level, the holes can be injected from or to the metal, and P-type effect or P-type organic field effect transistor is realized. Okay, the idea is the Fermi level of your source and drain contact must be close to your HOMO, so that the carriers can be hop into and out from the channel to the source drain contact. For N-type effect, when you have a positive voltage applied to the gate, so when you apply positive voltage, you are inducing negative charge carriers at the organic semiconductor insulator interface. So the source drain metals, the Fermi level must be close enough to the LUMO level of the organic semiconductor. So electrons can be injected from the source drain metal or N-type source drain metal. Thus, the N-type is being realized. If the Fermi level is too far below, okay, you won't have enough energy, the electrons will not have enough energy to hop into the channel or out of the channel. Okay, it must be close enough to the band, which is this LUMO band. So if you realize for organic semiconductor, the carriers are more like hopping compared to inorganic semiconductor. In inorganic semiconductor, electrons, once they achieve that certain energy, they will just flow. Okay, it will be continuously flowing. But for organic semiconductor, it requires higher energy. This is because of the structure of the atoms itself. Okay, if I will show the structure later on, it is not ordered, not crystalline like the one that we have for silicon or other types of semiconductor. Okay. So this one I have explained. Weaker intermolecular interaction results in a much larger intermolecular distances in organic semiconductors. Furthermore, the more complicated geometry of organic molecules means that the complicated structure, the crystal structure itself, makes it very difficult for the electrons to move around. So these factors make the charge transport within the organic semiconductor taking place dominantly in a hopping mode, which requires much higher energy. Okay, like I have mentioned, the Fermi level must be close enough so that the electrons can hop. Similarly, for this one, the Fermi level must be close enough so that the holes can be transported into the channel. So although there have been a very low mobility achieved, obtained for organic semiconductor, but then they have improved the carrying mobility. So far, there is a vast improvement, maybe 10 or more than 10 order of magnitude. Okay, why? Because scientists keep on exploring new materials. Okay, organic semiconductor is something that you can create using a synthesizing process. You can engineer it, okay, and improve material processing, the fabrication process, whereby because organic semiconductor it is very low order of in magnitude, so need to make sure that there are not many defects being created. Okay, so that's why they have to improve the material processing. At the same time, the device architecture optimization, like what I have mentioned, the top contact, bottom gate. Maybe there are other types of architecture which is much more suitable in order to achieve higher mobility. Okay, so this is the different types of organic materials that scientists have explored. For example, from pentacene, they have engineering into other types of organic pentacene derivative. Okay, so I do not know what is the IFPS tips. So from one basic material, they have make it a different types of derivatives of that. Okay, in order to improve the performance. So in the end, they achieve a very good switching device. Okay, mobility increase. Just now it was 1, now it becomes like 40 or 50 cm squared per volt second. So far, that is the latest achievement for organic semiconductor. But then there are some challenges for organic transistor. One thing is many PFAT are being explored. Okay, they have used PFAT often to produce the field effect transistor compared to N-type field effect transistor. Because the N-type organic semiconductors in general still lag behind in terms of carrier mobility and air stability. Okay, one of the challenge of organic semiconductor, especially the N-type, the stability in air is very poor. So when it is exposed towards oxygen, humidity, it will degrade. Example, if let's say the performance is the mobility that you have achieved today is 10 cm squared per volt second, and if you measure again tomorrow, and it will degrade to perhaps 1 or 0.1. So we have to have a very good way to store this kind of device, but then it's not practical. Okay, device engineers, previously they have used the organic devices. They try a similar packaging like silicon. They use nitrogen to package this device, but then they realize that this type of air degrade the performance of the transistor. Also, another type of challenge is that the low mobility. Okay, why it has a low mobility for organic is that you are not like a perfect crystal like silicon. So organic semiconductor, the structure is not periodic. You have lots of defects and grain boundaries, they call it, grain boundaries. Maybe in between one grain to another grain, there are boundaries. So this will hinder the movement of electrons from one atom to the next atom. So that's why it's lower down the movement of transport of the electrons in the channel. So the low mobility of organic semiconductors is due to their poor crystalline quality and due to weak interaction between the electrons and the periodic potentials involved. And they tend to be amorphous or polycrystalline in nature. So consequently, their mobility will be lower than the conventional inorganic semiconductors. Okay, so you have to understand this as well, the crystalline order of organic semiconductor. Okay, so I have finished organic semiconductor. Any questions? This one I will share in a short while. Any questions so far?
Doctor, so basically now the organic FET is only used for like OLED screens, right? For now.
At the moment, yes, but then interestingly, there's an increased interest for biosensing for life sciences. as well. But it's not, it's still in research. Okay, there's a potential application over there as well.
So once it overcome the mobility issue, then it can be a potential biosensor, right?
Biosensor. But then for biosensor, you don't need to have a high mobility. You just need to sense. Once it can be able to sense with a certain types of voltage tolerance, then it's a good device. Okay, for biosensor, mobility is not the characteristic that we measure. For biosensor or any types of sensor, gas sensor or any types of chemical sensor, first thing is the sensitivity, right? So how sensitive is this device towards that analytes that we are measuring? Okay, first is sensitivity, second is selectivity. Okay, selectivity means if let's say your gas sensor, you claim that your gas sensor can sense oxygen. So if let's say carbon dioxide comes into the device, does it detect? Ideally, it should not detect lah. It can only detect, or if it's oxygen, just oxygen sensor. So that is a selectivity. Okay, and the third one is how small volume of sensor that it can detect, the limit of detection. Okay, for biosensor, for example, you said that you can detect certain viruses. Okay, is it until the virus is filling the whole room that only it can detect, or it can only detect only one virus is enough? So this is the limit of detection. Okay, and the fourth one is what is the maximum amount that it can detect? Some sensors, if once it detect this much, then it will just deteriorate, the performance deteriorate. So mobility doesn't come into the sensor characteristics. Okay, so that's why I'm saying that this organic semiconductor has a very high potential for sensor, okay, life sciences applications, because one thing is it's wearable. You can deposit on fabrics. Okay, you can just put into your skin. Perhaps it can detect your glucose from your sweat, okay, from your perspiration. These are the potential things that I have been reading so far, but it has not, I don't know whether they have marketed this or not. Okay, any other question? No? Okay, I think I need to do some revision for your test. I didn't do any discussion, right, about the test?
No, not yet.
Okay, what I will do is tomorrow, the first thing, I will just discuss about the test answers so that you will more well prepared for your final exam later on. Okay, so how you should answer certain questions, how you should avoid, what things that you should avoid, and so on, so that you know what to do, how to do better for your next exam now, which is the final exam, because we only have one test, right? Okay, and I want to ask, what is the progress of your group project?
So my group already plot out the IV characteristics and already did comparison already.
Okay, good, excellent. So you have to compile them and put it into the template that I have shared you earlier, the Electrical Journal of Electrica. Okay, you can start writing the report lah.
Okay, okay.
Okay, so the next phase is only submitting of your journal. Okay, so you start from the introduction, your literature review, your methodology, and your results. And this journal, you can the maximum or the minimum page is only about 3.5 is okay. 3.5 page double column. Okay, so if you have 4 members, 3 to 4 members, so you can just work together lah to come up with this. Because this course, there's no second test, heavily rely on this group assignment. Alright, so what I will do tomorrow is, tomorrow I will cover the test discussion, and then after that I will go to group by group to check your progress. Okay, very short, just a short discussion within the groups, okay, to see your progress. Then after that I will cover the last topic of this course. Or perhaps I check the discussion. No, I discuss the test first. Then I go to the notes. Okay. After I finish the chapter, then I will go group by group for the discussion of your project. Can or not? So because tomorrow is 2 hours, right? Hopefully I don't have any meeting. So normally Thursday I have meeting. I will just have to skip the meeting. Okay. So make sure every one of you prepared with something from your group lah. Okay, before you submit into the e-learning. Have you checked the final exam date?
Yeah, already checked.
Okay, so can you let me know when is the final exam for this paper?
July.
Okay, thank you so much. 6 July 2021. Is it in the morning?
9 o'clock morning.
All right, excellent. So that I can... Yalah. So next week is going to be your final year project punya presentation, eh? All right. So I'm not going to kacau you. I just want to finish up with your group work. The submission will be later on. Okay, you just focus on FYP2. Right? Can?
Okay.
Okay, any question regarding this, regarding final exam later? Final exam later we can discuss. Okay, if there's no question, we will end the class here. We will see you, I will see you next week. Sorry, next week lah. I'll see you tomorrow. Okay, thank you.
Thank you, Doctor.
Thank you, Doctor.
You're welcome.